Morning. Hi, Maria.
Yeah, good morning, everybody. Hi, Dave. Good to see you.
I'm going to stop sharing this slide and let you take the intro slides. Okay. You want?
Yeah, that's fine. So, for some reason, I see the slides in Meet Echo, but I don't see them in the room. So let me try again. Ah, now it works. Okay, David, should we start?
Yeah.
Okay. Then, hello everyone, and welcome to the Maprg session. I'm happy to be here and actually see some faces, and I also see Dave's face, so that's great. And let's start right away. Luckily, we got a 2 hour slot and we got some really nice presentations, so we should have plenty of time today. Yeah, so this is an IRTF session, but we also have a note well. It's very similar to the IETF note well. And if you're not familiar with it, you should look up the respective RFCs maybe. Um, this session will be recorded and will be found on YouTube later on, so please be aware of that no matter if you're in the room or a remote participant. Then also the IRTF follows very similarly the privacy policy and the code of conduct of the IETF. So basically, this is just a reminder to be nice to each other, to work together in a friendly way, and also for all the presentations, state your questions clearly, stay friendly, and most usefully for this session, provide productive feedback if you have some. I said this already. This is not an IETF session. It's an IRTF session. So what we do here today is mostly inviting researchers to present their work and building a bridge between these communities to the IETF. Okay, this slide is usually just here. So if you have the slides in front of you, you have a quick link to everything you need to know or you don't know yet. Just as a reminder, because this is our first hybrid meeting, the people in the room are also supposed to use the virtual queue, and you can join the queue over the Meet Echo interface, either the light interface or the full interface. Both is accessible over the agenda. And more importantly is you have to please join, even if you're in the room, one of these two ways to join the Meet Echo session, because that's also how we generate our blue sheets. So if you're in the room, please join the Meet Echo as well, so you're noted in the blue sheets. Yeah, and like Dave, if you don't have anything else, basically, we start our presentation from here. Perfect. Then our first speaker is actually in the room, just arrived, first time attendee, and we're very happy to have you here. So Hamas, if you want to come in front, and I'm getting up the new slide set for you. If you press this, it should do something, which it doesn't. Oh wait, I have to acknowledge that. Now it can select the slide. Oh no, okay, wait, sorry, I did this wrong. What can I? This is yours. Okay. Jetzt kann ich neu.
Okay. Hello, everyone. Can everyone hear me fine? I'm Hamas bin Tanveer, and today I'll be presenting my work called Glowing in the Dark. So this work is in collaboration with Raji Singh from Microsoft Research, Paul Pierce from Georgia Tech, and Rishabh Nityanand, who's my PhD advisor. So just to give you an overview of where this work fits in. So as everyone knows, we have IPv4, we have IPv6, but then we have scanning in v4 and scanning in v6. So scanning in V4 is very well understood. There's been a lot of studies about it, and people basically know how to measure it and how to do it. But things are not the same in V6. So we know that V6 is a much larger address space, and scanners basically need to figure out where these active spaces of addresses are before they start scanning. So there's been previous works on trying to figure out how to measure scanning in IPv6, but there's been no work on measuring how scanners in the wild, like what techniques they use to scan active regions of IPv6 address space. So I'll get a bit into what scanning is and then move to IPv4 and IPv6 and then go on from there. So yeah, so scanning is basically sending unsolicited communication to an IP address in order to draw a response, and it can be done for a lot of different reasons. So reasons both malicious and benign. But in this talk, we're more concerned about not concerned about what scanning is, but how scanning is different for IPv4 and IPv6, and why is that the case? So scanning in IPv4, so there's a lot of tools for that. So for example, if you use Zmap, you can scan the entire IPv4 address space within a matter of minutes, obviously given that you have a good enough internet connection. But in IPv6, things are not quite so simple. Because the address space is now 2 to the power 128 total addresses, you just cannot brute force it. So what you have to do instead is you have to come up with newer scanning techniques so you can go through the IPv6 address space trying to find addresses that you previously didn't know of. And these newer scanning techniques is exactly what we characterize in this paper. So just to hammer in the point that how bigger the IPv6 space is in relation to IPv4. So this image helps me hammer it down really well. So let's say if all of the IPv6 address space were equivalent to the 4.5 billion years the Earth has been in existence, the IPv4 address space would equal 2 trillionths of a second, or the time that light would take to traverse the period at the end of this sentence. So basically, you just cannot brute force it. It's not really possible. So given that this IPv6 space is so large, how do you even start to scan it? So right now, there's two major techniques that you can use. So one is called IP scanning, and the other is called NX domain scanning. So in IP scanning, what you do is that you go to these public sources of IP addresses like DNS zone files or Tor relay consensus data or NTP public servers. You get all these addresses, you try to figure out patterns in them, and then you generate newer target addresses to scan. So basically, what ends up happening is that by learning patterns in these IP addresses from public sources, you reduce the search space where you want to look for newer IP addresses. But NX domain works very differently. So NX domain scanning basically involves exploiting semantics that were described in RFC 8020. So I'll go into a bit of how what is defined in RFC 8020 and how it works. But just to make sure that although the search space is reduced for both of these scanning techniques, for IP scanning, the results are still probabilistic. So you might find 10, you might generate 10 more addresses, but you still cannot be 100% sure that they are actual addresses which are allocated. But for NX domain scanning, you will always get an IP address that is allocated. So what is RFC 8020? So RFC 8020 is called NX domain. There really is nothing underneath. So and so one of the main clauses in this RFC is that an NX domain response for a domain name means that no child domains underneath the query name exist either. So when you apply this RFC to DNS reverse trees, it unintentionally presents a side channel for efficient scanning of the IPv6 address space. So let's say over here, if you have the IP6.ARPA, which is the root for DNS IPv6 reverse zone trees. So let's say if my DNS resolver is basically set up to to uh, reply NX domain for if something does not exist under a tree, and let's say I look up 0.ip6.arpa. So I will end up getting an NX domain. This means that I no longer need to care about 0.ip6.arpa. So I will go to 0 till E, and when I reach F, I'll finally get a no error. But for all others, I'll get an NX domain, which means I can just cut all of those subdomains out. I don't need to care about all of them. So now I'm only left with F. So now I can proceed with 0.f.ip6.arpa, and I can just go on until I've reached the whole /128 IPv6 address.
So
So
we have somebody in the queue, but usually we take questions at the end, or do you want to take it right now?
I'm happy to take it right now.
Okay, go ahead, Peter.
Hi, it's Peter from the ESEC. Actually, I don't mind
Mhm.
asking in the end also, but so my question is, this reverse inference technique only works when um, the IP addresses actually have reverse delegations and records in
Exactly.
the DNS. I wondered if it's known what the fraction of that is.
So there has been prior works which kind of try to learn newer addresses using these techniques, and the amount of addresses that they generate. So I'm not sure about the actual number, but it was a lot. But there's no kind of study about how many of the total IP addresses have a reverse domain attached to them. But that's a really nice point. We can kind of like incorporate it in future studies. Okay. Oh, yeah. So just to put this into perspective of a /64 subnet, so this is the subnet where a host resides in IPv6. Let's say I am a scanner and I want to find that little green dot that you see at the top, and that's the whole, that's the 128 IPv6, the whole IPv6 address. So now I have two /65s over here, so one on the right and then one on the left. So I know that my address resides in the /65 on the left. So I end up sending queries to both, and what is going to end up happening is that the right part is going to return NX domain, but the left part is going to return no error. So now I know I only need to focus my efforts on the left part of it. So I'll do the same for the /66s on the left. So what ends up happening is that I get NX domain for the part on the bottom, but no error for the part on the top. And I do this for /67s, 8s, 9s, till I reach one /127s. And in the end, basically, I reach the whole /128 IPv6 address space. So what this ends up doing is that it reduces the number of potential probes from 2 to the power 64. So basically one for each IP address in this host space, down to just 64 total probes to get to the actual address. And this is a significant exponential decrease in the amount of probes that you need to send to find a host inside a /64. Okay, so now I'll talk a bit about the experimental setup. So there were a few goals that we had in mind, which were motivations from the previous studies that were trying to study scanning in IPv6. So most of them were basically based on studying IPv6 scanning in darknets, or uh, from a vantage point of an authoritative DNS server. But the problems with that was that most of the scanning activity they got was as a result of IPv6 misconfigurations, or they could not link the activity inside the IPv6 address space to the scanning activity that came in. So for this experiment, we wanted to mimic an active IPv6 address space, capture actual scanning traffic, so nothing from misconfigurations, and link scanning activity to the services that were deployed in this IPv6 address space. So, oh, so just to give you an overview of how my experimental setup, so the grid that you see, so this was supposed to come up one by one, but I don't know what happened. So the grid that you see, so this is divided up into 4/58. So one of them is used to run our services, and the other three are control ones, so nothing was ever run in them. And these are all the services that we run for the entirety of our experiment. So the reason for running these services is basically to incite scanners to tell them that yes, this is an active address space, and you should look for stuff in here, because we kind of give them a signal that yeah, we are running stuff in here, and you're likely to find more addresses near, because you just simply cannot brute force everything. So we capture all DNS and reverse DNS lookup logs and all the incoming traffic from a router that was pointed here. And then we had two types of address assignments for each of our services. So each service was deployed, had 4 instances, and they were never deployed in the same /64 subnet, and not in this in adjacent subnets. And each service had two lower byte assignments and two random assignments. So lower byte assignments are addresses that people put up manually just to remember IPv6 addresses. So they will have a lot of zeros in the start and like a couple nibbles at the end with a value like 1, 2, just to remember the address. And the random assignment does not follow this pattern. So it's a random string of numbers throughout the subnet, throughout the interface identifier. Okay. Yeah. So some of the key observations that we saw that so our method of measuring scanning activity, so we did see scanning activity even before we ran any of our services, but the main point was that scanning activity increased significantly after services were deployed. And this increase was not only in terms of the number of scanners, but also in the number of probes that we see. And the main observation that we made was that NX domain scanners are using the side channel very, very effectively. So in this graph, you can see that we have the duration of our experiment on the y-axis and the subnet IDs on the x-axis. So 00 to F8, so it's 256 in X. So the green highlighted portion basically shows our /58, which had services running in them, and the other part is the control part. So this is the part before any of our services were deployed. So right now you can see that NX domain scanners are kind of like guessing, even the IP scanners are guessing, but NX domain scanners probably think that there is something in the start and the end of our subnets, and IP scanners think that there can be anything everywhere. But the important part comes in when we deploy our services. So as you can see in the for the NX domain scanners, they never go outside the /58 line. So they know exactly where the services were deployed and they stay inside that. Because to basically cancel out every other subnet, they just need to send in one request to each of those subnets. If that returns an NX domain, they can just cancel that out. So they don't even need to check them. So for the entirety of our experiment, they only stay within that /58. And on the other hand, IPv6 scanners, they constantly search the entire 256 subnets, trying to look for new addresses. So this basically tells us that the RFC 8020 semantic is actually being exploited by a lot of scanners right now, which reduces their search space by a lot. And this is our results for all of the services that we ran. So just to give you, just to like explain what this means. So for example, if you see wget and 511, that means that the mean number of scans per subnet that was running the service wget got 511 more scans uh, after the service was run as compared to before. So delta diff basically means that the increase in scanning activity was within the treatment subnets, so where the services were running. And delta C says that this increase in scanning activity was in control subnets where nothing was running. So some of the key takeaways we have are that NX domain scanners target treatment subnets for almost all the services. They target control subnets much less. And IP scanners kind of exhibit mixed behavior. They target both treatment and control subnets because they don't really have an idea. Every time they want to scan something, they have to go deeper and deeper inside the subnets themselves to figure out if there's an address in it or not. On the other hand, NX domain can just send one request. If it gets an NX domain, it can just wipe out the entire subnet. And NX domain scanners target different services than IP scanners. So as you can see, all of these services are kind of targeted by NX domain scanners on the left, but IP scanners only seem to care about DNS probes, NTP servers, and DNS zone files. So some of the key takeaways we have are that analyzing dark traffic is really not the best way to study scanner behavior, particularly in V6, where you need to give out a signal that yes, there is something active going on in this address space to invite those scanners. And then most scanners aren't really using NX domain scanning, but we think that this is only a matter of time. And one question I pose here is that is the efficiency from NX domain responses worth the loss of defense against scanning? So RFC 8020 was initially introduced to improve the efficiency of caching of DNS trees. So if the side channel gives you much easier access to scanning, is it really worth it? And then address discovery methods are very different than we expected. We expected that people will go to scanners will go to these public lists of IP addresses like Tor, NTP, get addresses from there, and then scan. But they don't really do that. They mainly rely on open DNS resolvers. And then neighboring networks should expect scanning activity. So let's say if a /64 subnet has something running in them, we expect that the neighboring /64s are much more likely to receive scanning traffic due to something running in that /64. And so we have a lot more takeaways and a lot more results, but due to time constraints, I couldn't put those in. So if anyone wants to discuss those, I'll be happy to do it. And if anyone has any questions and comments, I would love to take them. Thank you.
Yeah, thanks a lot. And we do have a queue. You can see it over there.
Oh.
It's all virtual these days. So Alexander.
Thank you. Thanks for an interesting presentation. Alexander Mayer from Nick.at. I was wondering, did you also look at whether all name servers actually implement RFC 8020? Because that has been a big discussion in the DNS working groups.
Mhm.
And actually, you would prevent that malicious activity by having a DNS server that is not compliant to RFC 8020. Do you have any figures on that?
So the only thing that we made sure for our experiment was that our DNS server was implementing RFC 8020 because we want to figure out whether people are kind of are exploiting this semantic. But we did not look into how many servers out in the wild are using this.
Yeah, okay, because I suppose that many name servers for IPv6.ARPA would actually be some kind of database generated backends that could easily fake things.
That's true. That's true. That can be done.
Interesting operational
Yep.
insight. Yeah, thank you.
That's a good idea. Thank you.
Rafi, welcome. So also on 8020, pretty much it was a long time to get this actually done, to have the kind of answers be more kind of the next domain answers to cover what is underneath. And if you don't want to have something in the reverse tree, either just don't put it in or put everything in.
Exactly.
Because that's what a lot of people do.
Exactly.
So, I mean, I would not go back to not having 8020.
Yeah. So this is one of the defense techniques that we actually want to propose in this paper, that just if you want to comply to RFC 8020, just make sure you put off the scanners, because this technique has been also discovered in many other papers that you can discover a lot of IP addresses using this. So one of the defense mechanisms against scanning would be that just everything that someone requests for, just give an answer for that. Just give no error for that. And yeah, that's, thank you.
This is Peter Koch. Hi. Again on 8020. I'm wondering a bit, the scanning technique was actually described as early as the 2005, and maybe before 2005 was when Roy Arns and I had a paper about this and a couple of other things. And also we described some mitigation techniques, but this was much before 8020. 8020 suggests that resolvers implement the semantics, but conceptually these semantics were already there.
Yep.
So if you bypass the resolver, that scanning technique is available anyway. So any recommendation in dampening or mitigating 8020 is probably not achieving very much, because you can always bypass that and do the scanning. But happy to take that.
Yeah, sure.
Thanks.
So just to talk a little about it. So what the previous speaker suggested, that you can just basically return everything, something for everything that someone asks. So that can be one of the defense techniques, but obviously you can still kind of bypass that. But I'll be happy to take it offline.
Petr Špaček. The thing is that the defense is actually one line in the zone file, because you can define wildcard in the reverse tree. So everything is compliant, but because you define the wildcard, you can return, just an, I don't know, TXT record saying, well, nothing is here, but this wildcard will prevent synthesis of the next domain.
Yeah.
So please don't say that RFC 8020 is wrong. It's correct, but you have to configure the zone file correctly.
So there's a study by Tobias Feiberg, and he basically discovered that, I think, addresses in the range of a couple million that were previously not known from other scanning techniques. So I would imagine that in the wild, this is something that people are not configuring in a way that you just suggested. So in this paper, we want to basically tell them that please just do that. It's very simple. You can achieve a lot more defense against scanning. Yeah.
Okay. Thank you a lot.
All right. Thank you so much.
Nice to have you here. And we're switching over to some DNS related topics. Our next speaker is Moritz Müller, and you should already be set up and can start, right?
Yes. Can you hear me okay?
Yeah, we hear you very well.
Perfect. Yeah, hi, and welcome to my presentation about the DNSSEC deployment metrics research. This is actually not a measurement study, but a study about measurement studies. This was initiated by ICANN, and we are carrying out the study currently together with the folks from NNet Labs. In short, the goal of this research is to identify metrics and techniques that can be used to measure DNSSEC deployment now and in the future. And finally, to recommend then ICANN metrics that should be measured to obtain the most comprehensive view of DNSSEC deployment on the internet. And today, I would like to give you some background about this project, share some of the challenges that we face with categorizing and inventorizing all these different metrics, and finally to hear from the measurement community, which they think are the most important metrics to measure DNSSEC deployment and which are the most adequate techniques. Let's dive right into the challenges. The first challenge is that DNSSEC deployment is a very wide field. If you start thinking about metrics to measure DNSSEC deployment, and you probably come up right away with two things: how many domain names are signed with DNSSEC at the root, top-level domain names, and second-level domain names, and so on, and how many resolvers actually validate DNSSEC signatures. But if you think about this only a little bit longer, then you already come up with many other metrics. On the signing side, that could, for example, include what kind of algorithms are being used for signing a domain name, or is a domain name does a domain name roll its keys frequently? Is it using NSEC, NSEC3, or does it support some other kind of DNSSEC automation? On the validation side, you again might think about the algorithm. What kind of algorithm does the resolver support? What kind of trust anchors does it have configured? Does it support some kind of signaling protocols, and so on and so forth? Additionally, the DNSSEC protocol is still being extended, or at least related extensions are being deployed and developed. This could, for example, include CDS and CDNS key records, where operators can automate the deployment of DNSSEC. So do these attributes also should be measured in order to get an idea about DNSSEC deployment? And finally, we have the challenge that there are also other protocols related to DNSSEC. First thing that comes into mind is DANE. Should it also be taken into account when measuring DNSSEC deployment? The second challenge is related to the measurement technique. Each or almost each of these metrics can be measured in different ways. When we think about, for example, whether a resolver is validating or not, then we could use active measurements, for example, from Web Atlas, and issue queries to the resolvers of these Web Atlas clients, and then see what kind of response they get. Another approach would be to look into traffic collected at an authoritative name server, for example, see whether a resolver is requesting DNSSEC records, and from that derive whether a resolver might validate or not. And both of these approaches have its pros and cons. Then, of course, we can not only look into different recursive resolvers, but we might want to look into the client side, whether a client is using only validating resolvers or not. Other metrics might include whether we rely on a measurement platform like the mentioned Web Atlas, or we use our own measurements setup where we use the standard libraries and use our vantage points that we have control of, or we use some kind of hack where we, for example, use a proxy network and then use this proxy network to issue queries from these clients. Other aspects might include whether we have access to raw data, or whether we actually have access to aggregated data. This, for example, includes our ASAC data collected from the root servers, and whether we have full control of the measurements, or whether we rely on a third party to collect the measurements. And all these different attributes of these measurement techniques have, again, influence on the metrics that are being collected. So for this reason, in order to address these challenges, we have the following approach. The first is to get a very broad overview of which metrics have been measured so far by the community. And there we mean not only the academic community, where we look into academic papers at more the high level, high tier conferences and journals, but we also look into more conferences where industry partners are also presenting, so that we not only cover the people that actually publish their studies at academic conferences and journals, but also other contributions as well. These conferences then include RIPE conferences, of course, ICANN DNSSEC workshops, ORG, and so forth. Then we want to carry out a gap analysis, where we want to understand whether there are still metrics that have been not covered by related work so far, that we use basically our own expertise in DNS and DNSSEC measurements. And finally, to develop an assessment framework to assess the different measurement techniques and to understand which of these measurement techniques are most useful to measure a certain metric. I want to say a few words about the assessment framework. That's probably a big word, but in the end, we of course want to focus on the coverage. How many, for example, resolvers can we potentially cover with a certain measurement technique, or how many domain names we potentially cover. But we think in order to have measurements that measure DNSSEC deployment that are also useful for a broader community, we also have to look into other attributes of these measurement techniques. These include, in our opinion, the reproducibility. To what extent are the parameters known of the different measurement techniques? And can we reproduce the results actually independently? And also whether these measurement techniques are actually feasible to roll out at a larger scale. So for example, of course, it is not very hard to measure the DNSSEC deployment of domain names if you have access to all the zone files, but the chance that you have access to all the zone files is not very likely. So we also want to take this into account when assessing the different measurement techniques. And with that, I already come to my end of the presentation, where I would like to collect feedback from you as a measurement community and would like to understand which DNSSEC metrics do you think are most important to assess DNSSEC deployment now and in the future? Does that only include well, how many domain names are signed, for example, and how many resolvers validate, or do you think that also more advanced, so to say, metrics are necessary? And finally, if you would think on which basis you would select a different measurement technique, which would that be? Would you only solely focus on coverage, or do you think that other aspects are important as well? I'm not sure how much time we have for questions, but I will hang out in the chat and you can reach me at this email address if you want to. Thank you.
Yeah, thanks a lot, Moritz. Yes, we have a little bit of time. We have one person in the queue already.
Thank you, Moritz. Interesting presentation, a lot of interesting aspects. To answer your first question, I think that what I would like to know is, on a global scale, how many DNS transactions are actually being protected, or what is the percentage of DNSSEC protected transactions on the public internet? That's because that's what in the end actually counts. It's a single figure, combines popularity of a domain name with the DNSSEC population and validation population.
Mm-hmm.
But that in the end is the end-to-end metric to me. Thank you.
Okay, thanks, Alex.
Yeah, I mean, actually, thanks for bringing this presentation here and starting discussion. Feel free to have more comments on the mailing list, have a discussion there. But I think that's also very interesting to maybe take a similar look at different measurement studies and more broadly figure out these kind of aspects. So very nice to have this discussion in this group.
Thanks, will do.
Okay, but if there are no other questions, then I think we just move on. Okay, next we have Jerome Mao. Great to have you here. I've just set up your slides and I think you should have control and you should be ready to go.
Yeah, thanks. So can everyone hear me?
Yeah, we hear you well.
Oh, sure. Thank you. Yeah, so this is Jerome from CWRU, and today I'm going to present our results in measuring the support for DNS over TCP in the internet. Right, so here are the topics I'm gonna cover today. So I'm gonna look at the DNS over TCP support on two sides of the DNS infrastructure, the recursive resolver side and authoritative DNS server side. So
we just lost your audio for some reason. Can you still hear us, Jerome? That's a problem. Can you hear us? We lost your audio. And you lost our audio.
Oh, I can hear you.
Okay. Now we can hear you again. So we missed a little bit of what you said, so I think you have to go back a little bit. Oh, and you're gone again.
Jerome might be accidentally muted.
I'm not sure if that's either a meet echo problem or a problem on your side.
I think it might be worth doing a hunt for mute buttons, both hardware and software.
Oh, yeah, I was muted and I don't know why.
Yeah,
Okay.
now I see that you're unmuted again.
Now.
Okay.
Okay. Yeah. Okay. So yeah. So I think I'm back. All right. So at the end of the talk, I'll...
Go ahead. I think we're fine.
Yeah. So at the end of the talk, I'll just briefly talk about the race condition between the race recursive resolvers.
And we lost you again. Okay. What do you think it is, Brian? Yeah, can you hear us? We lost you again, and maybe it might be your local AirPods or something that mute you or something like that.
I can hear you. Yeah. Oh, let me take off my...
Yeah, let's do that. And you have to start again at the top of the slide. We didn't hear anything.
Let me take off my AirPods.
Okay, that also doesn't work. Now you sound like a robot. Do you have some different headphones maybe available? We can't hear you again. Let's actually switch the presentations and we come back to you and you can figure out if you can get some other headphones. Because if we don't hear you, that doesn't help. Mike, would you be ready to just take your presentation first?
Yeah, sure thing.
Perfect. Sorry, I'm just trying to find your slides and have problem about that as well. So.
Okay, so is screen sharing also an option?
You can give it a try, yeah.
Okay.
Oh no, actually I have your slides. If that's easier. Sorry about that.
So if it's possible, I would like to check if screen share is working and fall back with the PDF.
Yes. Okay, now we see an empty screen.
Okay, perfect. Let me check.
Okay,
Now that should
that works. Perfect. Yeah, go ahead. And welcome.
Thanks for having me today. So I have some echo here. Maybe from the room, I'm not sure.
Yeah, maybe the easiest thing is just mute the room for yourself.
Ah, okay. Yeah. Okay, now the echo should be gone. Yes, perfect. Okay. Yeah, thanks for having me today. So I'm mostly blind and I can't hear you. So maybe we take questions following the presentation. All right, let's get started. So hi, welcome. I'm Mike from Technical University of Munich, and I'm going to present our paper on DNS over QUIC, which was a study we performed and was accepted at PAM conference, which is scheduled to happen next week. So let's start with the brief history of DNS transports. In the 80s, we had unencrypted DNS with DNS over UDP and DNS over TCP. So those have these obvious problems with eavesdropping and on-path manipulations. And then we have a shift to the encrypted DNS with DNS over TLS and DNS over HTTPS, which suffer mainly from the drawbacks of the TCP protocol, like multi-RTT handshakes and head-of-line blocking. And this is addressed by DNS over QUIC. DNS over QUIC is in its final standardization stage. And the main feature is the feature of QUIC, which combines the connection and the encryption into a 0 or 1 RTT handshake. So there are a lot of experimental implementations for clients and servers. And they are also used in production systems. For example, companies like Edgard or NextDNS already offer public DNS over QUIC services. However, there are no studies focusing on DNS over QUIC, which we did in our study, where we first looked at the adoption on resolvers worldwide, and then on the response times of DNS over QUIC. So starting with the adoption, we performed weekly scans over 29 weeks of the IPv4 address space, and we also scanned for DNS over UDP to have this as a baseline. As for DNS over QUIC, we support the DNS over QUIC versions draft 06 to draft 00. And for QUIC, we have support for the RC version and the 3 different draft versions, which are stated here. In our adoption scans, we collected different metrics. First of all, the negotiated DNS over QUIC, as well as QUIC versions, and the common names of the certificates. So this is a distribution here where we have highlighted in the different colors different combinations of DNS over QUIC as well as QUIC versions. So let me guide you through this figure. We see that the adoption rises slowly but steadily. So from the first week of our measurement to the final week, we see an increase of around 46% to 1,217 resolvers. But what we also see is a high fluctuation. So only 52% of the resolvers which were available in the first week are still reachable in the last week. If we compare this to DNS over UDP, we have around 97%, which are still reachable in the last week. Also, we only observe 7 pairs of DNS over QUIC as well as QUIC version. And it's important to note here that we added support for QUIC version 1 in week 43 only. So the ones with QUIC version 1 are highlighted here in the dark blue bars. We can also see that in the final week of our measurement, the DNS over QUIC as well as QUIC versions are dominated by this combination of DNS over QUIC draft 02 as well as QUIC version 1. We also see an uptake in the weeks which are highlighted here of QUIC version 1 in combination with DNS over QUIC draft 02. And we could track this to the open source DNS server implementation of Edgard Home. So they changed their default QUIC version from draft 34 to QUIC version 1. in this week. And we could verify this also by looking at the common names of the certificates. So we find something like edgard.something.something, which hints at the usage of the Edgard Home open source DNS server implementation. So next to their open source DNS server implementation, Edgard also offers a publicly reachable DNS over QUIC service. And they already implement DNS over QUIC to have 0.3 in combination with QUIC version 1, which is highlighted here in the yellow bars. And we find these for around 25 resolvers in the final week of our measurement with the common names dns.edgard.com and edgard.ch. Next, we come to our response times. So for our response times measurement, we performed hourly measurements over the course of 1 week, and we used the list of IPv4 addresses from the adoption scans. We performed a single query per protocol, and it's important to note that we have a location bias why we only measured from one vantage point. And this is why we did comparative measurements to DNS over UDP, TCP, DOT, and DOE. So in total, we find 246 resolvers which support all those targeted DNS protocols. Then we perform 2 subsequent queries. The first one is a cache warming query to warm the DNS cache, and then the actual measurement. We collect different metrics. We have the handshake time, which is the time from the start of the connection establishment until the connection is established, be it secured or unsecured. Then we have the resolve time, which is the time from the time we state the DNS query until we get a successful answer back. And the sum of both is the so-called response time. More than that, we also have a protocol-specific RTT. So we performed protocol-specific RTT measurements with different payloads per transport layer protocol to get an estimation of the RTT, which could be different based on the payload you are using in the different transport protocols. As for limitations, it is important to note here that we do not support TLS session resumption or early data in the study, which is what we are currently working on. Starting with the response times. So first of all, we have to check our expectations. The resolve time, as it's just a DNS query, then the answer from a cached record and the DNS answer, as well as the RTT, which should take roughly 1 RTT over all protocols. And if we now look at the resolve time here in the CDF, we can see that all different protocols overlap. So we find that resolve times are identical as expected. Moreover, if we now look at the protocol-specific RTT measurements, which are shown here in the subplots, we also see that all protocols overlap. So we find no protocol-specific path influences here. And if we would overlay those figures, we would see that the resolve times and the RTTs are actually identical. So our expectation of 1 RTT for resolve time and for the RTT measurement is confirmed. We next look at the response times, also starting with the expectations. So for DNS over TCP, this is just the 3-way handshake. We expect 1 RTT. For DOT and DOE, the TLS handshake is added to the TCP handshake, which should take 1 RTT on TLS 1.3, so in total 2 RTTs. And for DNS over QUIC, we expect 1 RTT due to the combination of the encryption and the transport handshake into 1 RTT. And if we look at the handshake times here on the right-hand side in the CDF, we see that DNS over TCP here highlighted in green on the left-hand side actually shows the fastest handshake times. If we now look at DOT and DOE on the right-hand side, they are overlapping. They show the slowest handshake times, and DNS over QUIC is somewhat in the middle. So DNS over QUIC falls short of DNS over TCP, but it improves on DOT and DOE. What we can now do is we can have a look at the handshake to RTT ratio. So as said, we also measured the protocol-specific RTTs on every handshake time measurement. So we can divide the handshake time measurement by the RTT measurement to get the handshake to RTT ratio, which is shown in the subplot here. And what we can see for DNS over TCP to the left-hand side here shown in green is that this nicely aligns with the one RTT as expected. So this is confirmed. If we now look at DNS over TLS and HTTPS, again overlapping here on the right-hand side, we see that it follows the distribution of two RTTs up until the median, and then it converges into a long tail. So this is somewhat confirmed. And for DNS over QUIC, we see a very weird distribution here. So around 20% of measurements follow the one RTT distribution, and then it converges into a long tail, where we see around 40% of measurements have an handshake to RTT ratio of more than 2 RTTs. So analyzing this, we find that this is an interaction with the QUIC client address validation, which is a mandatory feature of the QUIC standard to prevent traffic amplification attacks. So we actually did perform client address validation while we reused the token which was issued by the DNS over QUIC server issued in the cache warming query and our subsequent initial of the actual measurement. So according to client as well as server state, the client address validation is actually fulfilled. However, what we find is that the handshake is still limited by the traffic amplification limit. So the server stops sending if 3 times the amount of data received by the client is reached. And depending on the size of the X509 certificate, the certificate either fits into its limit or it exceeds it. And if it fits, everything is fine. If not, we have one additional RTT for the handshake. This is actually not specific to DNS over QUIC, but a quick implementation bug of the resolvers we targeted. So as a conclusion, we see a slow but steady adoption with high week-over-week fluctuations. As for our response times measurement, we find that QUIC's full potential, or DNS over QUIC's full potential, is utilized in only 20% of measurements, where 40% of measurements show considerably higher handshake times due to the client address validation behavior. However, despite the still unused optimization potential, DNS over QUIC already outperforms .do. And this is why we conclude that performance-wise, DNS over QUIC already is the best choice for encrypted DNS to date. So we have a lot of more detail, more analysis in our paper. We open sourced our code and data sets, so please have a look there. Thank you for your attention, and I'm happy to take questions.
Yeah, thanks a lot. We have Lawrence in the queue.
Can you hear me now? If you unmuted the room?
Yes.
Okay.
Yes.
Lorenzo Coliti, Google. Super interesting. And I'm part of the Android networking team, and we're actually in the process of rolling out something that you didn't test, actually, which is DOH3.
Mm-hmm.
So basically DOH over QUIC, right? And one thing that's related to this is that seemed to be like easier to implement because there's more server support. And one thing that we noticed is there's a substantial hit in terms of bandwidth due to lots of HTTP headers that really substantially increases the bandwidth used for the queries. And it would be interesting if you had that type of measurement as well, because metrics on Android are, few thousand DNS queries per day, and it sort of adds up. So I'd be super interested in seeing what metrics you have, or what metrics you could get with, in terms of bandwidth size, because you measured RTT, and that's super interesting, but also like how much bandwidth is used by these queries, because that's a big deal. So just wanted to say that it's also super interesting work. I'll share this with the team that's working on this, and in particular, like the QUIC bug around, I will be looking at the paper to see if there's anything we can do about that. I wasn't aware of this issue, so we're going to be looking at that. Thank you for presenting.
Okay, thanks for the comment.
Yeah, thanks a lot from my side. Again, like you can always have further discussion on the mail list. I don't see anybody in the queue. I think we still have network problems with Jerome, so I think we just move on in the agenda. And that means Jörg would be next up.
Can you click the slide?
I can click the slide, so you can click it there if you want. Okay, that's fine.
So, hello everyone. My name is Jörg Deutschmann, and I'd like to present some performance measurements of quick implementations over geostationary satellite links, which we have obtained using the Quick Interop Runner. This presentation is based on a preprint which is available on arXiv, and I have to emphasize that this work was actually done by Sebastian Andres, but he has finished his thesis recently, so that's the reason why I'm presenting this here. Next slide.
Sorry.
So geostationary satellite networks heavily rely on TCP proxies, or so-called performance enhancing proxies. These are not applicable anymore in the case of encrypted transport, so like VPNs or QUIC. And so far, the performance of QUIC over geostationary satellite links has shown to be very poor. There's a draft which summarizes the most important aspects. We have talked about this in previous Maprg meetings, and there's also a literature overview. However, so far, tests were limited to specifically selected quick implementations. So the question remains, how do other quick implementations perform over geostationary satellites? Next slide, please. You're probably all aware of the Quick Interop Runner. For those who are not aware, here's a screenshot of it. It was developed and is maintained by the Quick Working Group and especially Martin Seemann. And I have to say a big thank you for providing this framework, which helped us to integrate our satellite scenarios. Next slide. So the Quick Interop Runner is obviously mainly used for interoperability tests and standards compliance. But there are also two performance tests which use a very non-challenging link, a symmetrical link with low data rate, low RTT, and no packet loss. In the good put scenario, a 10 megabyte file is downloaded, and the performance is quite good for almost all implementations. There is another performance test where there is one competing TCP flow, and the results show some significant unfairness. So what we basically did is add satellite-related performance tests shown in the table at the bottom right. First, the terrestrial scenario is very similar to the Goodwood scenario, except that we use a link rate of 20 megabit per second in the forward link and 2 megabit per second in the return link as a baseline for most of our scenarios. Then we have the SAT scenario, which has a RTT typical for geostationary satellites. We have the SAT loss scenario, which has an additional random uniform packet loss of 1%. And then we have two real satellite operators, Astra and Eutelsat. This required some modifications to the Interop Runner, which we will see in the next slides. And what we also did was the generation of time offset graphs, which we will also see in the next slides. Next slide. So very brief, the architecture of the original Quick Interop Runner. It consists of Docker containers running on a single host machine. NS3 is used as link emulation. We have 12 quick client implementations and 13 quick server implementations. And for each combination, we run 10 iterations. And this setup is used for the emulated scenarios, terrestrial, SAT, and SAT loss. So on the next slide, we see the modified architecture, which integrates real satellite links. In our case, the client host and the server host is located on different machines. So the client host directly connects to the satellite modem, whereas the server host is located in our university network. And the main modification is then that the client and servers are interfacing with real interfaces. There's only a single vantage point, so it's not very representative, but it's mainly used to check how well does the emulation setups compare to the real satellite links. Yeah, next slide. Okay, so let's have a look at the results. On the left side, we see the satellite scenario with a emulated forward link of 20 megabit per second. The first thing to note is that in Legend, the scaling goes up to 10 megabit per second, so it never exceeds 10 megabit per second, although the link capacity is 20 megabit per second. The timeout for one experiment is set to 2 minutes. So after 2 minutes, we abort the test, which is denoted as a red T. In case of any other failures, we see a red cross. The server implementations are shown in the columns, and there you can see that mainly IOQuick, KWick, and Nginx is performing rather poor, whereas the client implementations are shown in the rows, where KWick, MoveFast, to some extent Niku, and NGTCP2 are not performing that good. In general, we see very mixed results. On the right side, we have the SAT scenario, but with an additional packet loss. And you can clearly see that the performance decreases. We have a lot more timeouts. Also, the timeout was set to 6 minutes in this scenario. And actually, there are only a few combinations which perform okay. Okay, next slide. Then we have the real satellite links. On the left side, we have Astra, which again uses the baseline of 20 megabit per second in the forward link. Results are again mixed. Some implementations work quite well, some don't. I won't go into details here. Maybe on the right side, we see Eutelsat, which has a link capacity which is twice as much as the other scenarios. From looking at the legend, you see that the absolute good put values are slightly higher, but compared to the link capacity, the higher the good puts are still not very satisfying. Okay, next slide. Then we have a summary of the results considering all implementations. We use as metric the link utilization defined as good put divided by the link data rate. And here you can clearly see that the satellite scenarios are way beyond the terrestrial link. In terms of absolute numbers, Eutelsat has the highest values, but again, compared to the link capacity, it's not really beneficial. The higher link capacity is not really beneficial. Okay, so next slide. Now we try to understand why the implementations perform differently. We try to look into which congestion control algorithms are the implementations using. So this table is not guaranteed to be 100% correct. We try to look at the code and the command line parameters and the documentation. Then we created a correlation plot, which has the link utilization of the SAT scenario on the x-axis and the link utilization of the SAT loss scenario on the y-axis. You can clearly see that the implementations which are using Reno or near-Reno do not perform well in the SAT loss scenario. Regarding Cubic, there are few, most implementations perform well in the SAT loss scenario with a few exceptions, and BBR performs equally well in the SAT and the SAT loss scenario. What we did not look at yet is the impact of flow control, which of course is also important, especially regarding because when the client has limited flow control, then the server cannot do much about it. Okay, next slide. To further understand the behavior of the implementations, we try to automatically create time offset diagrams. This was not possible for every combination due to various reasons, but I've picked 4 exemplary time offset diagrams which we can look at. So the first one on the next slide. So we have 10 iterations, and the iteration with median and finish time is highlighted. So here we have KWig as server and MSQuick as client. You can see that the slow start takes very long, roughly 10 seconds, and this is a problem for many combinations and implementations. We then see kind of a bursty behavior, and we see that the sending rate of a few iterations significantly differs from the other runs. Yeah, next slide. For the next example, we're still in the SAT scenario without artificial loss, but we see many retransmissions marked as orange points. What's interesting here is that at 5 seconds, the offset numbers are not sent continuously, so there are gaps in sending the offset numbers, and these gaps are then transmitted at 6 seconds. So the two parallel lines at 5 and 6 seconds are not retransmissions at 6 seconds. So we do not have really an idea what's going on in such implementations. On the next slide, we have an example of the SAT loss scenario, and this is actually an example which works very well. We have PicoQuick both as client and server. We have a very quick ramp up. We have the retransmissions due to the packet loss, and we have speculative retransmissions at the end, which is probably very helpful for such high latency links. Okay, next slide. We have another example which does not work that well, MSQuick as server and XQuick as client. So you can see that the sending rate goes up and down a lot, and the overall time is, yeah, it takes really long for transmission of a 10 megabyte file. Okay, so the summary: we have modified the quick interop runner. We included emulated satellite links and real satellite operators, and we also automatically generated time offset diagrams. The key message is probably that quick over geostationary satellite links is still performs very poor. It's worse with packet loss. The performance depends on both client and server. Of course, some implementations might be proof of concept implementations. They are probably not optimized for satellite links, but we also saw a great variation. Some implementations do okay, others do not that good. For us, it was very hard to debug each and every implementation or combination in detail, simply because there are quite a lot of implementations. But as next steps, we try to do some more detailed analysis, maybe consider the influence of the flow control at some further test scenarios and long-term measurements, because we think that the interop runner is really helpful for us to test the performance of a broad range of quick implementations. Yeah, in case of any discussions, I'd like to welcome you, to invite you to the E2SAT mailing list. Thanks.
Yeah, thanks a lot. Very interesting. So you keep trying to debug or look into implementations, finding out what the problems are. Are you also talking to the implementers directly?
Yeah, we have received some feedback already, which is very, very good. But like really understanding the code of every implementation is just, yeah, takes a lot of time.
Yeah. Okay, we have a Q Hamas.
Hello, Hamas, University of Iowa. So I do understand that a very interesting talk, first of all. So I understand that the performance is very poor for quick and geostationary satellites, but so can this study be kind of like transferred over to lower Earth orbits or something like Starlink? And what would that look like? Like, would quick still perform very poor because now you're connected to a satellite for, let's say, 6 minutes at max, and then the satellites keep on changing. So how would this study transfer over to lower Earth orbits
Yeah.
satellites?
Thanks for the question. We actually have some performance measurements with Starlink already there on the website. Starlink in general performs quite well. It does not have the problem of the high latency. So yeah, it seems to work better, but we're also interested in making quick work over geostationary satellite links.
But aren't there still problems with every 5 minutes as that satellite changes? So you have that additional handoff time. So whenever
the
the
handover.
satellite comes in, would that affect these measurements?
We don't know yet.
Okay,
We
all right.
try to look into this, but
Lorenzo Caviti, I'm just really out of curiosity if you've taken any sort of suggestions to the quick implementers, like about what to do. Like one like obvious and probably very stupid thing to do is if the latency is more than 500 milliseconds, just be a bit more aggressive, because like that doesn't happen on wired links. But I don't know if that's like just really stupid or only stupid. So that's just really out of curiosity. Like what, have you thought about what to do? You've got the data, right? So it would be good, I'm sure you're sharing the data with them, but also like if you said, hey, like if you could experiment, for example, like see, hey, this works, this doesn't work. Just out of curiosity again, maybe you've done nothing. But.
So the if statement in the code, like I am on a satellite link, actually PicoQuick does do this. There are other approaches which have been discussed in the quick working group
And it works?
yesterday.
It helps?
It helps.
Ah, cool.
PicoQuick is one of the better performing implementations over satellite links. So there are other approaches like the zero RTT BDP approach, which was discussed in the quick working group yesterday. And of course, you have to do parameter tuning, and then the question is how does a good congestion control algorithm look like for such kind of links? So these are all very basic questions. But it already helps if the implementations simply add a satellite test case to their benchmark scenarios. That would really help a lot, because a lot of papers and so on, they simply don't consider this kind of link, which is a bit sad. And I hope to motivate the quick implementers to have a look at this kind of links.
Very interesting, right? I actually have my own high latency link. It's not a satellite link, but it's and I had to write my own performance enhancing proxies for TCP, and So thank you, very interesting.
Thanks.
Okay. Yeah, thank you, Jörg. I think that's the end of the queue, and we move over to Matthias at this point.
So yeah, hello everybody. And this is a talk about Quick and DDoS scanning. Oops.
Just take it out.
Easier. Yeah, hello. This is a talk about Quick and the measurement study that we conducted last year to better understand whether Quick is used to conduct DDoS attacks. And this joint work with Marcin, Raphael, and Thomas, and was presented last year at IMC. So next slide, please. So in a nutshell, the main takeaway of this message is we asked the question, is Quick used for DDoS? And the answer is yes. And we measured this based on data from a network telescope. So now I want to present you a little bit more in details. Next slide, please. So just as a brief recap, Quick is based on UDP and has typical UDP properties. So usually it does not have states, and is based on UDP because to prevent ossification attacks. On the other hand, it has also some properties inherited from TCP because it needs to actually implement states. It is connection oriented, and this leads to some vulnerability. Next slide. So one of the main design decision or options for Quick was to actually delay, to reduce delays on the one hand, and on the other hand, to make it robust against a typical denial of service attacks.
And the typical quick handshake looks like this. Client sends an initial message to initiate the handshake, and the server responds with the initial message with the server hello and the TLS handshake. And after this first round trip time, a client can already send data to the quick server, and the server will reply. Next slide, please. Yeah, so the point here is that the server replies to a source, even though the source is not verified, which is very important. So next slide. And this behavior makes a quick server vulnerable to two types of attacks. The first attack is a reflective amplification attack. What is the idea here? The idea is that the attacker sends an initial message to a server, but use a spoofed source address. And the server will reply to the spoofed source address. And instead of sending one packet, it will send two packets. So the server actually reflects the initial message and amplifies the initial message. Question here is whether this is a likely attack. Next slide. And the answer is it's rather unlikely. It may happen, but it is unlikely because Quick by design allows its client only a server only to reply 3 times more volume compared to what the initial client was sending. We heard this already in the previous talk. First and second, so it is limited, amplification volume is limited by a factor of 3. And second, there are many, many more UDP-based protocols available that allow for much higher amplification factors, such as DNS or NTP. So this is a possible attack, but by design is limited and rather unlikely. Next slide. The second type of attack that the attacker might conduct is a resource extortion attack. And the idea here is that the attacker sends an initial message, again, using spoofed source IP addresses to allocate states at the server side, and the server will reply as usual within the first round to type with the initial message and the TLS handshake message. And this is sent back to the source, to the spoofed source IP address. And ideally, this source address does not, is offline, so it will not reply at all with a reset or something like this, which means that the server allocates states for a decent amount of time. And if the attacker has a distributed botnet, for example, and floods the server, the local queue at the server will fill up, and the server will not be able to reply anymore or even to benign requests. So, and in addition to this, to allocating state, it also introduced computational resources because of the cryptographic TLS handshake. Next slide. And these replies from the server to the spoofed source IP address can be observed, and a typical measurement infrastructure to observe spoofed packets are network telescopes. And these telescopes actually will receive packets that are spoofed with IP addresses from the network telescope IP prefix. In our measurement study, we leverage this telescope, such a telescope. Next slide. What we actually did is that we analyzed data from the UCSD/CAIDA telescope, which is a /9 IP prefix, so a rather large address space, which allows us to capture more than 2% of the actual IPv4 address space. So this is only focusing on IPv4, as we heard in the previous talk. Measuring malicious traffic in an IPv6 space is a different story and much more complicated. And we did this for a whole month in April 2021. And this telescope receives a lot of malicious traffic. It's not only quick scans or a quick backscatter, but also TCP scans, TCP backscatter, and so on. So next slide, what we did is we need to distinguish this quick traffic. And how did we do this? We did first a port-based classification. So we filtered for all UDP 443 traffic. And this is a very common method to distinguish quick traffic from other traffic. But we also applied some kind of deep packet inspection to exclude false positives. And for this, we used the Wireshark dissectors. And we also did some manual verification. So we were very sure that the traffic that we identified were actually quick traffic.
And based on this network telescope and our method to identify the quick traffic, we detected 92 million quick packets. And then we distinguish this or split this traffic in two types, request and response. So requests are packets that are sent to the UDP 443, and responses are to the destination port UDP 443, and responses are packets that included the source port UDP 443, and requests are packets that are more or less scans. I mean, as we heard, researchers do scans, for example, to find quick servers, and the responses are backscatter traffic, so traffic that was sent from a quick server back to the spoofed IP address, so response. Okay, next slide. When you then what you see here is a high-level view on the traffic that we captured. On the x-axis, you see the time, and on the y-axis, the number of packets. And we saw two heavy scanners, which were from TUM. We heard about it, and the other one was from Aachen. And then some other traffic remains. So we excluded the scan traffic because it is not of interest at all. And in 2022, we also saw some scans from Census. So the commercial scanners were a little bit late compared to the actual research scanners. So that was the sanitizing, including all of the scanners, because this traffic is benign, but we are interested in the malicious part. Next slide, please. What you see here is now the traffic that we captured after sanitizing, distinguished between response and requests. And for the request packets, you also see a little zoom, a little inlet here. This is the blue curve, and this shows more or less a diurnal pattern, which most likely are still scanners, but not the heavy research scanners, maybe malicious scanners that looking for quick servers, but with a much lower weight compared to the heavy scanners. More importantly, is the orange curve, which shows the response packets. And here you see a very, very erratic pattern. So you have a quick increase in terms of packets, and then a quick decrease, which is a typical pattern for denial of service attacks. Next slide. Then we checked who actually is attacked. Who receives, or from which autonomous systems do we receive the responses, which means where is the server located that receives the spoofed request. And that you see in the second column, responses, and each line shows you the type of autonomous systems where the responses comes from. And the vast majority of responses that we receive in our network telescope are actually located in content provider networks. So next slide. Now the question is whether these responses to the source address from the source address are actually denial of service attacks or something else. And this is in general a challenge. Identify, I mean, you see a lot of traffic. Is it an attack or not? And what we did here is that we applied a common threshold from prior work. So first, we group all packets in sessions, and each session is split by an idle timeout of 5 minutes. And then we applied this common threshold, which means that we identify a session as an attack if the session lasts longer than 60 seconds, and if we see more than 25 packets, and the maximum packet per second rate of 0.5. So, and next slide, applying this, we found actually more than 2,900 attacks in our measurement set of these 1 month. And surprise, surprise, next slide. The majority of victims is actually are Google servers, and the other rate is relates to Facebook. So most of the attacks
go to one of these famous content delivery or web services. Next slide. And now you can ask, I mean, this is identifying the attack is somehow based on empirical data, whether our thresholds are valid or not, because they are from prior work some years ago. And what we did is that we changed these thresholds based on of different weights. So any that you see here on the x-axis and on the y-axis, the blue curve is the number of attacks that we identified based on the weight. If you have a weight that is smaller than 1, we have a more relaxed thresholds, and if you have a weight that is larger than 1, we have a more stricter threshold. And what you see, even if we put a much stricter, 10 times stricter denial of service threshold, we find still a significant, I mean, a decent number of attacks. And second, that is shown by the orange curve, that that's a share related to content delivery networks is, I mean, that the attack threshold is more or less independent of this. Next slide. And then we looked a little bit more in detail into the victims and to better understand whether a quick denial of service attacks relates or correlates with other attacks. And what actually can happen is that the attacker only attacks a quick service, that first another service is attacked and then the quick service, or that an attack of different services occur in parallel. So this is you see here illustrated at current attacks. The red triangles show the start of the attack, and the green triangle shows the stop of the attack. And the first column shows you a concurrent attack, which means that the typical TCP Zinflood attack, for example, occurs in parallel to a quick attack. And after that, the quick attack continues, which means that you have a sequential attack. Next slide. And now we did a statistic of all events and found that half of the attacks are actually concurrent attacks, which means that we have a quick attack in a parallel TCP ICMP Zinflood of ICMP flood, TCP Zinflood, and roughly 40% of the attacks that we found are sequential attacks, which means after TCP Zinflood, a quick attack occurs. And only 9% of the attacks that we found were quick-only attacks. So, which basically means an attacker leverage all of the protocols that are available, even new protocols such as quick, to do resource exhaustion attacks at the victim. Next slide. Now the question is, can we protect against this? And there's one mechanism, which is a quick retry mechanism that allows these type of resource exhaustion attacks before a client is authenticated. And the idea here is to follow an approach similar from TCP cookies. Before the quick server establishes the state, it sends a cookie, a secret to the client, and the client needs to reply with this. And if this is correct, after that, the server starts the typical quick handshake. And if the answer is not correct, the server just ignores it and no state is established at all. And now I show you a brief emulation, or I mean a testbed evaluation, whether this quick retry mechanism helps to prevent resource exhaustion attacks. And what you see here is, I mean, what we used is Nginx and initiated actually quick floods towards the server, and based on different attack rates and different configurations. And what you see here is, in this configuration, if you have a packet per second rate of 100 packets per second, then you already will be able to make the quick service unavailable. Then next slide, you can argue that you can use more resources, more CPU resources. Yes, you can do, but still, I mean, if you increase the packet rate, you will be still able to turn the service offline, and the quick server will not work. So next slide. But if you enable the quick retry message, you will be able actually to prevent the server
from being exhausted, and the service will be still available. But on the back, the one is, important note here is that the quick retries message adds an additional round trip time. That is a little bit the disadvantage, but it prevents these type of attacks. So next slide. Yeah, very important. I mean, this evaluation that I presented here is not about Nginx. That is a design issue by Quick. What we found in our data is that none of the servers you actually currently use the retry options, most likely because the retry message adds additional round trip time, and you actually want to reduce round trip time and delays. Next slide. The data that I showed you was from 2021. We also analyzed more recent data from this year, and we found that these quick initial floods actually doubled, so attack volume increased. And we also analyzed Google and Facebook's off-net servers, so servers that are not located in the Google or Facebook areas. And if you consider this, you even find more attacks. It's currently not only Google and Facebook that are attacked. In our data set, we found also messages from Cloudflare. But luckily, I mean, some of the servers that are attacked use retry packets, even though that's a very, very small minority. Next slide. So to conclude, Quick is vulnerable against initial floods that try to do a resource exhaustion attack on servers. And we actually find this type of attacks deployed in the real internet with an increasing trend. You can prevent this and mitigate this by using retries. Currently, many servers do not use retry, but if you want to prevent this, you need to enable it or find another way. Okay, next slide, final slide. If you're interested in more details, there's a full paper linked here, including a publicly available PDF, and all of the software and artifacts are also available. Thanks.
Thank you. And we start with the queue, Alex.
Thank you. Very interesting information. Do I understand correctly that you said your telescope would catch about 2% of the potential backscatter of an attack?
Yes, because of /9. Yeah.
So that means that the attacks would probably be like roughly 50 times the size that you observe.
Will be, yeah.
And compared to other types of DOS attacks, those appear really, really tiny. Yeah, I mean, we are dealing in the DNS industry with tens of millions of packets per second. And my question is, you said you saw more attacks in terms of number of floods that were coming in 2022. Do you also see that the number of packets that are used in those attacks, the packets per second, are actually increasing? Because that would indicate to me that this is coming out of kindergarten and finally getting a real tool. Because quite frankly, I don't think that 100 packets per second would actually be noticeable on Google's side at all.
Yeah, I mean, I don't know the.
I think that was my sorry that made me think, is that maybe something like a gamma ray bit flip in a client that goes berserk on the server? So is it actually an intended attack? And what you said about the multi-protocol backscatter, that tells me a little bit more that it's probably a try by someone, but not really a professional attack.
Yeah, I mean, we are not arguing that the services that receives this data actually get offline or something like that. What we are saying is that we see, I mean, patterns that hints towards this attack. Whether they are successful or not is a different question. That is not what we are analyzing here. But it's a good point. I don't know the PBS for the updated data. Something that we should. I don't know now. I will check.
Maybe just research.
That's a good point. But I mean. This talk is more meant to be also be cautious. I mean, people are trying to explore this type of attack, and even though it's currently maybe a low data rate, it might increase in the future, and you should be prepared for this.
Right. But you're not seeing that the packet numbers or packet rates increased.
As I said, I don't know. I mean, I don't
Okay,
know it now.
yeah,
I mean, we did update the data recently, so yeah, I have to check this. Sorry.
Thank you. Excellent research. Thank you.
Really good research. So one of the things that we saw in our IPv6 scanners was that some scanners controlled, let's say, a /48, and they would send 2 packets from each of the IP addresses and then increment the address and then keep on sending 2 packets every time. So would your calculation of attackers miss that? So if someone's using some sort of a distributed architecture to send scans, maybe let's say if it doesn't send 5,000 packets, it just sends 10 packets from each IP address and then keeps on changing. And would your study
yeah,
capture that?
if you have a distributed
Yes.
type, yeah. I mean, it can be captured. No, that's not an issue.
Okay, so I forgot like exactly how you said that if these are the conditions are met, then we considered it as a scanner. So
I mean, if you can go back,
To where?
yeah. Anyhow, I mean, we group it by source IP address. Here,
yeah, the next one, I think.
next one.
Yeah.
Yes. By source IP address. And I mean, we did not do it here, but you can also consider requests or replies from multiple sources in parallel. And then you can track and emulate some of the state increase, for example.
Yeah.
So
Okay.
that is not an issue.
Yeah, makes sense. Thank you.
Okay, thanks a lot. So Jerome quickly drove to university and now has better connectivity, so we will give it another try.
Yeah, so can everyone hear me now?
We can hear you right now.
Oh, great. Thank you. And first of all, my apologies for any inconvenience. Sorry, I just moved to another place for a better connection. So I hope it sounds better now. Right. So this is Jerome from CWRU, and today I'm going to present our results. Oh, I'm hearing echoes.
You can just mute the room locally on your site, and we take all the questions at the end then.
Okay. Okay. So yeah. So today I'm going to present our results in measuring the support for DNS over TCP in the internet. Right. So let me see. Oh, yeah. So here's the topics we're going to cover today. So we're going to look at the DNS over TCP support on 2 sides of the DNS infrastructure, the recursive resolver side and authoritative DNS server side. So we focus on the support in those 2 sides because they are where we can directly associate the TCP support behaviors to the actors that are responsible for them. And at the end of the talk, I'll briefly discuss the race condition between the recursive resolvers and authoritative DNS servers in DNS over TCP. So let's move on to the TCP's fallback support by recursive resolvers. So later I'll just use resolver, which is the shorthand for recursive resolver or recursor. So the general approach is that we want to measure as many resolvers as possible. And we want to force those resolvers to talk to our ADNS through TCP. So what we did is our ADNS sent truncated UDP responses to the resolvers, and those UDP responses have no resource records at all. So therefore, if the resolvers want to complete the resolutions successfully, they are expected to fall back to TCP protocol. We have 4 data sets on those resolvers. The first one, an open IPv4 resolver scan with unique queries to our own domains. The second one, we use the bouncing message. We use the bouncing message in SMTP protocol. So our scanners send emails to non-existing recipients as the domains from the Majestic top 1 million list from our own domain. And those mail servers, they won't be able to successfully deliver those emails. And so they are expected to send bounce messages for the delivery failures back to our mail servers. So they have to query the MX records in our domain, and our ADNS are going to force the TCP fallback in those MX resolutions. The third data set, we use the famous RepAlice platform. So we let the RepAlice probes to send unique queries to our own domains through their resolvers. And the last data set, we have the ADNS logs from a major CDN. Those logs are highly aggregated, so we only use those logs to assess the real-world activity of the resolvers from different categories. Right, so here's a challenge. So when we are talking about TCP fallback, so TCP fallback is a two-step process, and it is hard to associate the DNS over UDP queries and DNS over TCP queries. And because of the collaborative resolution, it is even harder. So our definition for TCP fallback capable is that either a resolver itself is capable of fallback to TCP, or this resolver has a peer that falls back to TCP for it. So here I expect an animation here, but sorry, it's PDF version, so there's no animation. But just to illustrate what is a canonical scenario in TCP fallback, So if we've seen one UDP query from resolver and one TCP query and another TCP query from this resolver for a unique query, then we can say that this resolver is TCP fallback capable, and this is a canonical scenario of the TCP fallback. And the figure here shows a more complicated non-canonical TCP fallback scenario. So you can see that we have two UDP queries from resolver A and resolver B, and a TCP query from resolver C. So in this case, we do not have enough information to say that the TCP query from resolver C is a consequence of A or B's UDP queries. Then resolver A and resolver B are indeterminate in terms of the TCP fallback capabilities in this transaction. And in fact, the non-canonical scenarios, they are very common. Actually, in our data sets on the resolvers, only 46.8% of all the resolutions are canonical. And even for the canonical scenarios, 18.9% of those scenarios have two queries coming from different IP addresses. So UDP query from one IP address and a TCP query coming from another IP address. And for the non-canonical scenarios, sometimes it can be very complicated to match the UDP query and TCP query. So here I just listed two real-world examples here. So the first one, you can see that. So our scanner sent just one single unique UDP query to the resolver, and in our ADNS, it ends up with 5 UDP queries and 4 TCP queries coming from 6 resolvers. And in another example, the same, it's another unique UDP query queried by our scanner, and you can see that there are like around 4 UDP queries and 3 TCP queries coming from 3 resolvers. So you can see that like the UDP and TCP queries, their fallback relationships are not quite very obvious in those two examples. So we have developed an algorithm that tries to group the queries into clusters by their potential fallback relationships. And we assume that like the maximum gap between a UDP query and its real TCP fallback TCP queries is 2 seconds. So you might be wondering, so what is a cluster? So why do you split all those 3 different queries into 4 clusters? So cluster is a group of queries, and a cluster ends with DNS over TCP query. And in addition to that, 2 consecutive TCP queries in a cluster are preceded by at least one UDP query. So here we have 13 UDP and TCP DNS over UDP and DNS over TCP queries here, and we split them into 4 clusters. In the first cluster, you can see that we have UDP query number 1 and 3 and TCP queries 2 and 4. The TCP query number 2 is preceded by UDP query number 1, and TCP query number 4 is preceded by UDP query number 3. And also, we can say that like the TCP query number 4 is also preceded by UDP query number 1. But if we assume that the TCP query number 4 is the fallback for UDP query number 1, then we're gonna left the TCP query number 2 unmatched, so which is unlikely. So in this case, we say that, so we just assume that the UDP query number 1 is fallback by TCP query number 2, and UDP query number 3 is fallback by TCP number 4. So in this case, both number 1 and number 3 are TCP fallback capable. And in cluster number 2, this TCP query is not paired by any UDP query, so we just leave it as this. And in cluster number 3, it's obvious that like the TCP number 7 is the fallback of UDP query number 6, so quite obvious one. And in cluster number 4, it's a little bit complicated because there are several kind of potential pairs, and like we cannot find a way to perfectly associate the UDP queries and TCP queries, because there are 3 UDP queries but only 2 TCP queries. And so in this case, we just say that all those 3 UDP queries are indeterminate. We just don't know which UDP query is TCP fallback capable and which one is not. But finally, in UDP query number 13, it is not followed by any TCP query, so we can confidently say that this UDP query, this guy, is TCP fallback incapable. Right, so just like what we've seen in the previous 2 slides, so some DNS transactions, they just don't allow unambiguous inference of the TCP fallback capability, like in cluster number 4. So in this case, what we do is that we have 2 estimations. We have the optimistic estimation and we have the pessimistic estimation. And the only difference between those 2 estimations is how we process the indeterminate queries. So in optimistic estimation, we just consider the indeterminate as TCP fallback capable. So in this example, in cluster number 4, we just assume that like UDP query number 8, 9, 11 are TCP fallback capable, and our pessimistic estimation, we just consider them as TCP fallback incapable. And throughout all of our data sets, we have studied around 116,000 resolvers, and around 95 to 97% of them are TCP fallback capable. So we use a range here to represent the number of TCP fallback capable and incapable resolvers according to the optimistic and pessimistic estimations. And the TCP fallback capable resolvers, they contribute to around 96 to 99% of the CDN traffic from all the resolvers we've studied. So the takeaway here from the resolvers measurement is that there is a non-negligible number of TCP fallback incapable resolvers, and they are about like just equally active as the capable resolvers. So next, we're gonna move on to the TCP support by the authoritative DNS servers. So in those measurements, we're gonna act as resolvers. So we have the control over the transport. So the general approach is just we try to send TCP queries to the ADNS serving certain domains from a testing machine on campus. So only one vantage point. And we still have 3 data sets here. The first data set includes the domains from the queries handled by the resolution service operated by the major CDN. And we test all the ADNS listed for each domain. The second data set, we use the Majestic top 1,000 root domain websites, and we call those popular websites. And still, we test all the ADNS listed for each domain. The last data set, we have a list of CDN accelerated domains, and we just pick one domain per CDN. And we test out the ADNS list for each domain. Here's the results for the ADNS server side. So first of all, the domains from the queries handled by the resolution service operated by the major CDN, more than 5% of the domains, they fail to resolve TCP queries through some ADNS servers. And still, like even for the popular websites, it's still like around a little bit more than 3% of the domains, they fail to resolve a TCP queries through some ADNS. And even for the CDNs, 11 out of 47 CDNs we've studied, they have deployed ADNS servers that do not support DNS over TCP. And so for the rest of the ADNS that do support DNS over TCP, we're gonna move on and see the race condition that are related to those do support DNS over TCP. So so first of all, RFC recommends reusing established TCP connections, and actually resolvers, they do reuse connections. In another email scan, we've successfully induced around 13.5% of the resolvers that serves the mail servers to reuse the TCP connections. So resolvers do reuse connections. And here's a race. If the server tries to close the connection after sending a response, and the server is trying to close out this connection after responding to this DNS query, but the client, the fin or the reset segment is still on the flight, and client doesn't know that like this connection is being closed out, and the client is trying to reuse this connection for further queries. We can see that this query is going to be left unresponsive. We're going to be left unresponded. So that's the race condition. And actually around 33% of the popular websites and for CDN providers, they deploy ADNS servers that just like close the connections immediately after responding to the first DNS over TCP query. So they are vulnerable to this race condition. Next, we are just trying to propose some optional update to the DNS over TCP, and we would like to put them here to discuss with the community. So there has already been a fantastic EDNS TCP Keep Alive extension, and this extension allows the client and server to dynamically negotiate the timeout of the current TCP connection. So maybe we can try to work more on this EDNS extension. So here are our proposed optional update here. First, a resolver must not reuse a TCP connection unless an explicit EDNS TCP Keep Alive negotiation has been completed. The second, the resolver has to be loyal to the negotiated Keep Alive duration. The third one, maybe we can just let the ADNS servers to retain the TCP connections for another 2 maximum segment lifetime beyond the negotiated Keep Alive duration, so that all the outstanding, all the DNS over TCP queries in the flight can be correctly acknowledged and processed. And there might be another potential optimization. We haven't studied on that yet, but it's just maybe we need more discussion on that. So a resolver, so maybe we're thinking like, so right now, EDNS TCP Keep Alive doesn't allow to be negotiated in UDP, but maybe we can try to let the resolvers and ADNS servers to negotiate the TCP Keep Alive in UDP, so that the resolver and ADNS are gonna know that, okay, so the remote endpoint do support or doesn't support, does support or doesn't support the TCP reusing. And maybe the client can try to shorten the previously negotiated Keep Alive duration here. And also because DNS over TLS explicitly borrows the connection management policy from DNS over TCP. So we hope that like these updates can also so we hope that like DNS over TLS can also benefit from these updates here. Right, so here's the conclusion for today's talk. First of all, on the recursive resolver side, a small but non-negligible number of resolvers, they do not support DNS over do not support TCP fallback, and actually they are very active, so they are under the risk of not being able to receive the answer for very large to receive very large DNS messages. The second of all, on the ADNS server side, still a non-negligible number of top websites and CDN providers, they use authoritative DNS servers that do not support DNS over TCP. And for the ADNS servers that do support DNS over TCP, many of them are vulnerable to the race condition. That's it.
Thank you very much.
Thank you.
Very interesting, and glad that we finally managed to get here in here. So did you try to reach out to the CDN providers and figure out if they're planning to support this or why they're not supporting this?
Oh yeah. We just we find some bugs in some CDNs implementations, and we reach out to them.
Okay. Yeah, definitely interesting to see these deployment numbers. So now we have somebody in the queue.
Yeah.
Hello, Lafiva Akama. So the question I have is the numbers you presented, you said some servers were not reachable. Did that mean that the resolution still could complete without TCP, or was it just kind of one of these or was all of these servers not responding with TCP? I mean, because some servers not responding from a user perspective is not a thing.
Yeah. Right. So some ADNS means like, so right. So if so maybe like they have two ADNS, one supports TCP, another one doesn't support TCP. So that means some, or like both of them, none of them supports TCP. So that's another like some ADNS.
Did you actually also calculate that number, because that would be much more interesting for real users?
Yes. I think we have the numbers. We have the numbers. Are you talking about this little bit more than 5% domains, or you are talking about the numbers on ADNS, but now the number of domains?
I mean, from my understanding, is these numbers just mean you have X domains that or X server that don't respond, but you don't have the amount of numbers, the number that actually would not resolve. That's a different outcome.
That would not resolve.
Because without without TCP, I mean, just so if you have a domain, say example.com, that has two name servers and one responds with TCP and one doesn't, then that would be still okay. Even it would be in your list of domains that where some are not responding, right?
Maybe you have to come closer to the mic.
Um,
Did you
yeah,
understand
can you
the
say that
question?
again? Yeah, can you say that again,
Okay.
please? Yeah, I am trying to follow.
So maybe just we take this
We take it offline.
offline, yeah.
Okay, yeah.
Yeah. We have Peter in the queue.
Hi. Yeah, I have a question on the interpretation of large samples of resolvers. So in fact, it's two questions. So I think your slide said you checked about 100,000 or so resolvers. And when we do resolver studies, we always wonder how like how much does that mean? Because if I find some random IP address that responds to DNS queries, it may be a resolver that is not actually used, or it may be, and yeah. So the first question I have is how to assess the significance or relevance of any given resolver, and that might lead to a bias in this 95 to 97% result if you would filter out the ones that aren't really real world resolvers and just leftover orphaned deployments or whatever. And the second question I have is similar. People sometimes argue that, especially in corporate environments, TCP support may be blocked by middle boxes or whatever, and that would be a problem for DNSSEC deployments and other things with large payloads in DNS. And maybe I didn't get it in your talk, but if you could point out one or two insights on that aspect and whether that is true or maybe not true about TCP support lacking in corporate environments. That would be nice. Thanks. And very nice research in general.
Thank you. So yeah, so first of all, let me try to repeat your question first. So your first question is, so you're saying like maybe some of the TCP fallback capable resolvers are not used, or some TCP fallback incapable resolvers are not used in real world applications. So how do we know that, right? Right. So we have the ADNS log from the major CDN. So we know that, like, so whether this ADNS is being used or not being used, and to what extent it is being used. And for this number here, you can see that, like, so we say that like around 95 to 97% of the resolvers are TCP fallback capable, and they contribute to around 96 to 99% of the CDN traffic from the resolver study. So that's our aggregated results here. So basically, that leaves like around so we cannot say that, like, so basically which resolver is being used and which resolver is not being used, but we can say that, like, so overall the TCP fallback capable resolvers are being used as this, and the TCP fallback incapable resolvers are still being used, because they still contribute to around like 1% of the CDN traffic.
Yeah, I think we have to take the second part of the question to the list. We are kind of at time. Sounds like an interesting question about blocking of DNS over TCP, which might need further study, and maybe just take it. Thanks again for being here and taking the effort to drive in the middle of the night to university. That's great to have you here. Thank you everybody else also who joined in the middle of the night. This wasn't a convenient time for everybody, but I think we had a great session. I'm so happy that we ended up in a 2-hour slot, even though we only requested 1 hour. Because we got some nice talks here. And I'm already looking forward to the next session. Dave.
Yep. Thanks, Maria, and thanks to the contributors too. You guys have a good week.
Okay, thank you everybody, and also thanking Alex for taking notes. That's it. Bye-bye.
The meeting notes and the videos should be available sometime.
Yeah, so the meeting notes itself are kind of already, so this is not like the final official version, but it's all here. So if you want to check on that, you can even edit it effectively.